Good morning, everybody, and thank you all for coming. So before I start, I would like to thank the organizers of this conference for organizing it and also for inviting me to give this mini course. It's a pleasure and an honor to be here. All right, so my assignment for this week is to explain to you what are Anosov representations. Okay, so let me start with some motivation. Okay, how I think about these guys. Okay. Okay, so I'm going to let Hn be the n-dimensional hyperbolic space, real hyperbolic space, okay? Okay, and there's a very classically studied class of group actions on this space, which are called the convex co-compact actions. Okay, so let me define them for you. So a discrete subgroup gamma inside of the isometry group of Hn, right, is convex co-compact. Okay, if there exists a non-empty convex gamma invariant subset C inside of Hn, okay, such that when you take C and you quotient out by the gamma action, you get something compact. Okay, and then you can slightly generalize this to talk about convex co-compact representations. So a representation or group homomorphism rho from gamma into isom Hn is convex co-compact. Okay, if it has finite kernel and its image is a convex co-compact subgroup. Okay, so of course, if you have a convex co-compact subgroup, if you look at the inclusion representation, that's a convex co-compact representation. Okay, now this class of subgroups of representations is very nice because it has kind of a very good combination of flexibility and rigidity at the same time. So, so what I mean by this, right? So this definition here is rigid enough so that you can prove some pretty strong theorems about this entire class of representations. But at the same time, it's flexible enough that it admits lots of interesting examples. Okay, so let me give you an example of so here's a theorem. Okay, so let rho from gamma to isom H be a representation from gamma to isom Hn. Okay, then the following are equivalent. Okay, so first, rho is convex co-compact. Okay, second, the group gamma is actually finitely generated. Okay, and the orbit map from gamma to Hn. Right, so what do I mean here? So I take any element in gamma, I apply my representation to it, okay, and I hit a point O inside of Hn with it. Okay, so this is for some or equivalently all O in Hn, right, is a QI embedding. Okay, so don't worry if you don't know what QI embedding means. I will explain what that is later. Okay, this is just a teaser. Okay, but you should just think of this as saying that this is what quasi-isometric embedding. What it's really saying is that the way that this representation takes your group and puts it inside of Hn preserves the coarse geometry, the intrinsic coarse geometry of gamma. Okay? Okay, so that's the second equivalent condition, and the third equivalent condition, so this is still part of the theorem, okay, is that the gamma is hyperbolic. Okay, and there exists a row equivariant continuous injective map, which I'll call C, right, from the Gromov boundary of the group to the visual boundary of Hn. Okay, so again, if you don't know what it means for the group to be hyperbolic or the boundary, what's the boundary, I'll explain later. Okay, but you should think of this basically, okay, so a group is hyperbolic means that, okay, in some, okay, just roughly, you can think of this as the group having some negative curvature properties, okay? And once this group has some kind of coarse negative curvature properties, you can define what it means for it to have a boundary. And it turns out that the gamma action on its boundary has some north-south dynamics, okay? And this statement here is saying that the way that your the representation here gives you a way to take the boundary of gamma and put it into the boundary of the symmetric space that preserves this kind of north-south dynamics, okay? So this is one theorem to kind of illustrate what I mean by the kind of the rigidity of this definition. Okay, you can prove, you know, you can describe what this class of representations or subgroups are using coarse geometry or using dynamics on the boundary. Okay, now there are also many other descriptions of this convex co-compactness, but for my purposes of this mini course, I'm also going to use this too. Right? Okay, so this is the rigidity part. What about the flexibility? Okay, so let me just show you some examples and also ways to build examples from existing examples. Okay, so of course the most obvious example is you take any uniform lattice in isom Hn. Okay, so in this case, the set C that you take is just all of Hn. Okay. Also,
can you say what a uniform lattice is? I used to not know that.
Okay, so this is a discrete subgroup of Hn, so that when you take Hn, you quotient out by the discrete subgroup, you get a compact, something that's compact. Okay. All right. Okay, so a second example. So I'm not going to be very detailed here, but I might say more later in the mini course. Okay, you can do a ping pong constructions here, so you can construct Schottky groups. The Schottky constructions. Oops. Okay, so this gives you lots of convex co-compact representations from the free group of any rank into isom Hn. Okay, so there are these examples as well. And then you can restrict to a quasi-convex subgroup. Okay, so I'll also explain what this is later, but this is a particularly nice class of subgroups of a hyperbolic group. Okay, and if you have a convex co-compact subgroup and you restrict it, or a representation restricted to such subgroups, then it's still convex co-compact. Okay, and then you can do like Klein-Musket combinations. Okay, so the way this works is if you have two convex co-compact subgroups inside of isom Hn, and suppose that they intersect along a subgroup that is quasi-convex in both subgroups, right? Then this gives you some conditions on when the subgroup generated by both of these groups is also convex co-compact. Okay, so there's some combination. And then finally, and this is sort of the most important in some sense, is deformation, deforming. Okay, and so another way to say this is that the space of convex co-compact representations is an open set inside of the space of homomorphisms. So the set of convex co-compact representations from gamma into isom Hn okay, inside of the space of homomorphisms from gamma into isom Hn. This is open. Okay, so if you manage to find an example of a convex co-compact subgroup or representation, you can perturb it a little bit and it stays convex co-compact. So this is very useful because it allows you to build examples that has generic properties, right? Because by deforming, you can make the representation satisfy some generic properties. For example, like Zariski density. Okay. Anyway, so this is what I mean by the flexibility that these representations have. Okay. So the question now is, can we find a similarly nice class of representations or subgroups, right, when we replace isom Hn, which we saw in the previous lecture, is an example of a non-compact semi-simple Lie group, right? When we replace, when this is replaced with some, with a semi-simple non-compact Lie group. Okay, and why would you want to do this, right? So, well, there are geometries that are not the hyperbolic geometry that are also interesting to study. Okay, and the automorphism group of these geometries, they are sometimes they end up being these non-compact semi-simple Lie groups. Okay, and so you want to see if you can develop such a theory so you want to find such a nice class of representation so you can study the geometry of this kind of so they can study these geometries that are not hyperbolic space as well. Okay, so that's the motivating question. Okay, so if you've never, I mean, if you're me and you look at this, so if you want to answer the question, the first thing I would try is I would just take my definition of convex co-compact and say, okay, I'm going to replace isom Hn with my semi-simple Lie group G, and I'm going to replace Hn with the associated Riemannian symmetric space. Okay, but what do you get then? So let's do a naive guess, okay? So I'm going to replace isom Hn by G. Okay, so this is a semi-simple non-compact Lie group. Okay, and then I'm going to replace Hn with M, which is the associated Riemannian symmetric space. Okay, so this is the G mod maximal compact that we saw in the previous lecture. Okay, and then use the same definition of convex co-compactness. Okay, so what happens in this situation? So if your Lie group is still of rank 1, so if the associated symmetric space is negatively curved, everything works. Okay, so everything works. If the rank of G is 1, the real rank of G is 1. Okay, but once your rank is larger than 1, then the situation radically changes. Okay, the existence of this higher dimensional flats in your symmetric space messes things up badly. Okay, so here's maybe a theorem. Due to Jean-François Kahn, also Kleiner and Lieb. Okay, so what they prove is actually much stronger than what I'm going to state, but this weaker version is easier to state and it already illustrates my point. Okay, so if G is a simple Lie group, with real rank at least 2. Okay, so you can think of PSL DR, where D is strictly bigger than 2. Okay, okay, and gamma inside of G is Zariski dense and convex co-compact. Okay, then it has to be a uniform lattice. Okay, and this kind of, so the Zariski dense condition here, you should think of it as just saying that, you know, your group is really sitting inside of G. It's not secretly sitting inside of some smaller Lie group. Okay, and this is telling you that, well, if you make this definition, you definitely cannot deform, right? These kind of lattices are very rigid. Okay, so you don't have the kind of flexibility that we want for our theory. Okay, so these are too rigid. Okay, so then the question is it hopeless, right? Are we dead? Okay, fortunately, I mean, the fact that that I'm giving this mini course tells you that the answer is no. Okay, and this is François Labrie tells you that Anosov representations are the answer. Okay, so this is kind of my approach to how I think about these Anosov representations. Okay, so that's just kind of the preview. Okay, but before we actually get into Anosov representations proper, unfortunately I have to do a bit of, I need to develop, I need to talk about hyperbolicity. So I'm going to spend the next maybe 20 minutes telling you what are hyperbolic groups and stuff like that. So if you already know what those things are, you can just take a nap, okay? And then wait for the rest of us to catch up. Okay, so section 1. Okay, so hyperbolicity of groups. Okay, so this works in, this is a story in the world of coarse geometry. Okay, so first let me define, make some definitions, some basic coarse geometry definitions. Okay, so I'm going to let x and dx and y dy be metric spaces. Okay, so first definition, if, okay, a map f from x to y is a CC quasi-isometric embedding. So I always abbreviate this as QI embedding. So big C and little c are both positive constants. Okay, if the following holds, if you for any pair of points x1 and x2 inside of the domain space X, what I'm going to do is I'm going to apply f to x1, x2, so that now you get 2 points in y, and I'm going to compare the distances. Okay, and I want these to be up to a multiplicative constant, an additive constant, and isometry. Okay, so more precisely, if you look at the distance in y between fx1 and fx2, this is bounded above by c times the distance in x between x1 and x2 plus c. It's okay. And 1 over c times the distance in x between x1 and x2 minus little c. Okay, so intuitively you can just think of this as, you know, if you stand really, really far away and you look at this map, right, it sort of looks like an isometry. Okay, up to this uniform multiplicative and additive constants. Okay, and then second, I say that this map F, if a QI embedding, okay, a QI embedding is a quasi-isometry, a QI. Okay? If it is coarsely surjective, okay, if there exists some constant b larger than 0, such that for any y in y, okay, there exists a x in x, you guys can probably guess what the statement is from the name coarsely surjective, right? If the distance between between fx and y, sorry, I should do a better job erasing. Is at most b. Okay, so this is what it means for QI embedding to be a quasi-isometry. Okay, and then maybe here's a fact, maybe to justify this name. Okay, so if f from x to y, in fact this is equivalent, so
can you write a little more to the right, Tengren? Because on this side it's hard to, like fact, I only see half of it.
Oh, okay, sure. So, okay, I'm gonna...
So that guy over there probably couldn't see it at all.
Okay, so I'm gonna keep away from this.
Yes.
This slip. Okay, so so the fact is that f from x to y. So okay, here this I'm assuming that this is a QI embedding. Okay, f from x to y is a QI. Okay, if and only if there exists a constant, say a, right, and a QI embedding. Okay, maybe I'll just write it a QI embedding f from x to y is a quasi-isometry if there exists a constant a and a QI embedding g from y to x, okay, such that the distance in x between g composed f of x and x is less than or equals to a for any x in x, and the distance in y between f composed g, y and y is less than or equals to a for any y and y. Okay, so this is usually what we call a quasi-inverse. Okay, so the existence of this quasi-inverse tells you that it's equivalent to being a quasi-isometry. Okay. Okay, so these are your analogs of, isometric embedding and isometry in the world of coarse geometry. Okay, so in particular, being a metric spaces being quasi-isometric is an equivalence relation. Okay. Okay, so let me make sure I didn't miss anything. Oops. Okay, good. So next, another definition is a coarse notion of hyperbolicity. Okay, so again, so I say that a geodesic metric space X is hyperbolic, okay, if for any triple of points x1, x2, x3 in X, okay, and for any triple of geodesics G1, G2, G3, geodesics in X, okay, such that xi minus 1 and xi plus 1 are the endpoints of GI, okay? the GI is then for any I. Okay, this geodesic GI lies in, I forgot the most important thing, this is delta hyperbolic. Delta here is a constant bigger than 0. If then this GI lies in this delta neighborhood of the union of GI minus 1 and GI plus 1. Okay, so let me draw a picture to illustrate what I mean. So this is my metric space X. I pick my 3 points. So X1, X2, X3. And then I pick my 3 geodesics. So maybe this is G3, opposite X3. This is G1, opposite X1. And this is G2, opposite X2. Okay? Then, you must have, if your space is delta hyperbolic, this means that no matter which triangle you pick like this, right? If you take the delta neighborhood of G3, okay, so, and the delta neighborhood of G1. Okay, so the union of this region here is supposed to be this thing on the right? This has to contain the geodesic between X1 and X3, G2. Okay? So this is what delta hyperbolicity is. Okay, and the key thing, of course, is that this constant delta is uniform over all possible triangles. Okay, so what are examples of these kind of spaces? So if you have a simply connected Riemannian manifold with sectional curvatures that are bounded away from 0, bounded below 0, okay? Simply connected Riemannian manifold with sectional curvatures less than or equals to some negative number. Right, these are complete. So the Hadamard negatively curved Hadamard manifolds are negatively curved, and then the sectional curvatures bounded away from 0. These are delta hyperbolic. So are hyperbolic. So when I write hyperbolic, I mean delta hyperbolic for some delta. Okay. A non-Riemannian example are metric trees. So any metric tree is metric trees are hyperbolic. Okay, in fact, these are 0 hyperbolic. So the picture you have is if you have a tree. Okay, and then you pick this vertex here. Let's say these 3 vertices, and you look at the geodesics between them, right? So from here to here, this is the unique geodesic. From here to here, this is the unique geodesic. Okay, you take a neighborhood. Okay, this contains the geodesic from here to here, which is exactly this. Okay, so this is actually 0 hyperbolic. Okay, the strongest kind of hyperbolicity you can get. Okay.
So this is like negative infinity curvature, right?
Yes. It's like if you rescale your metric, right, then you get that in a minute. Okay? All right. Okay, but what has this got to do with coarse geometry? Okay, so the point here is that this notion of hyperbolicity is really a property of the quasi-isometry class of the metric. Okay, so maybe I'll write this as a fact. Okay, so if X and Y are geodesic metric spaces, and F from X to Y, and maybe there exists a quasi-isometry F from X to Y. I'm sorry, I'm dropping a lot of chalk behind. F from X to Y. Then X is hyperbolic if and only if y is hyperbolic. Okay, so this is a good notion if you're working in the world of coarse geometry. Okay, so what else can you do with hyperbolic metric spaces? So you can define the notion of a boundary, which I mentioned earlier. Okay, so if gamma is a, not gamma, not yet. If X is a hyperbolic metric space, okay, then we can then it's a Gromov boundary. Which I'll denote by partial of X. Okay, is the set of geodesic rays in X okay, consider up to a certain equivalence relation that we call asymptotic. Okay, so what is this equivalence relation? So if you have two geodesic rays, right, gamma prime from r greater than or equals to 0 to X. So a geodesic ray is just a isometric embedding of this into X. Okay, and these exist by my assumption. Okay, so if okay, if these are asymptotic or equivalent. Okay, if the distance in X between gamma S and gamma prime S is uniformly bounded. So bounded as you vary S. Okay, so you know if two geodesics are going off to infinity, staying close to each other the whole time, right? Then they correspond to a single point in this space. Okay, so this is the asymptotic classes of geodesic rays.
I mean, with this definition, you don't need the metric space to be hyperbolic, right?
Yeah, you can make this definition, sure.
It's still pretty good.
No, but then it's not an equivalence relation.
This? Oh yeah, that's right.
Okay.
Yeah.
I'm not sure.
You need some
Maybe it's not the same. Maybe it's another definition. I cannot see.
No, okay. So the point is, if you want,
It's okay.
if you want to,
These two are close. Those two are close. Those
no. If you want, so okay. If you let's see.
I say bounded, then it's okay.
Yeah, if I say bounded, then it should be okay. I'm not saying going to 0. Yep.
Yeah, the problem is like linear growth or something.
Yeah. But when it comes to groups, then it becomes important later. Okay. Then also for these spaces, you can topologize this. Okay. So here's a fact. So first fact is there exists a natural topology on the boundary of X. Okay, and with this topology, X union the boundary of X is a compactification of X. Okay. The second fact is that if you look at the action of the isometry group of X on X.
What do you mean by a compactification?
Meaning that this is a topological space, a compact Hausdorff space, so that when you restrict it...
You need some assumption on X, maybe?
Sorry. X is my hyperbolic... Sorry?
If it is not in general, you have no assumption yet?
No, so X is my hyperbolic metric space.
Yes, but some compactness property at X that will show?
Oh, it needs to be proper.
Proper.
It needs to be proper.
Thank you, thank you. I should have written proper from the very beginning.
Yes.
Let's see, where should I add the proper in? Maybe there. Okay, let's here. Let's over here. Like this. Okay. All right. So here. Okay. So you can do this, and then here okay, everything here is under this assumption. Okay. And here the isometry group of X extends continuously. To an action on the boundary of X. Okay. And also the final fact is that if f from X to Y, so here X and Y are proper hyperbolic metric spaces. I should write that down. Okay, so if f from X to Y,
problem is both are compact.
yeah.
The closure.
Yeah. If f from X to Y is a proper hyperbolic metric space, okay, then f extends to a map boundary f, I call it boundary f, from the boundary of X to boundary of Y.
This is the thing that uses hyperbolicity of those things. All the other things are just true, I think, without hyperbolicity. I mean, the boundary of higher
This
rank.
one definitely needs hyperbolicity.
Yeah, that one definitely.
Yeah,
Those two. I mean, higher ranks metric spaces give you an example of what the phenomenon is like, right?
Like maybe you need like cat zero.
yeah, you probably need some.
Maybe cat
Some
zero.
assumption.
Maybe cat
Yeah.
zero. Okay.
F is a quasi-isometric entity.
That's right. Sorry, I should mention that. Yeah, f here is a. Sorry. Okay. Let me rewrite this.
Sorry.
Let me rewrite this. Okay. So let X, Y be proper geodesic metric spaces, proper hyperbolic metric spaces. Okay, and f from X to Y is a QI embedding. Okay, then f extends to a topological embedding. Which I'll denote by partial f from the boundary of X to the boundary of Y. Okay, and what do I mean by extend here? So extends here means that if you take a sequence xi that converges to X, where this xi lives inside of X, and this limit X lives in the boundary of X, okay, then this implies that your f of xi's, so this is now a sequence in Y, right, converges to the boundary f of X. So this is now inside of the boundary of Y. Okay? All right.
Can I just think maybe one final thing? When you say geodesic, we mean uniquely geodesic?
No,
No?
just existence of geodesic between pairs of points. And when you require the hyperbolicity condition, there's any.
I think that's the issue, though. It's not cat zero, it's that they're uniquely geodesic. Then things work. But when one says geodesic metric space, anyway, it's not important.
Okay.
Hyperbolic metric spaces are typically uniquely geodesic. This all works.
Indeed. I just, this is a lecture and...
Okay, so let's see. Is there anything else I need? No. Okay, so now I can introduce my group. Okay, so now I'm going to let gamma be a finitely generated group. Okay, with finite generating set S. Okay, then associated to the pair gamma S, you can define this metric space called the Cayley graph. Okay, so that's what I'm going to describe next. Okay, so definition, the Cayley graph of gamma S, right, is the graph which I'll denote by CS gamma, such that the vertex set of this graph is exactly your group. Okay, and the set of edges right, so when is there an edge between a pair of group elements? Right, this is if you can, from one group element, you can multiply an element in the generating set to the right to get to the other one. Okay, so gamma 1 inverse, gamma 2 is in S, or gamma 2 inverse gamma 1 is in S. Okay, so this is the Cayley graph. And then you can, okay, so right now this is a graph, but you can equip this graph with a metric by, okay, so first notice that there's a gamma action, gamma x on this graph on the left. Okay, and you can equip this graph here with a gamma invariant metric by making each edge, identifying each edge of your graph with the unit interval, okay, in a gamma invariant way. So identify each edge of the Cayley graph with the unit interval metrically, okay, in a gamma invariant way. Okay, and what you get is a gamma invariant metric. Which I'll denote by ds, depends on the generating set. Okay. Right, in fact, this metric is proper and geodesic. Oops, this should go here. Okay, and if you restrict this to the group, then this gives you a metric on the group. To a metric on the group is usually called the word metric. Okay. Okay. All right. So far, everything depends on the choice of a generating set. But now this is where cost geometry becomes useful. If I want to make something that doesn't depend on the choice of generating set. Okay. So fact is that if S and S prime inside of gamma are finite generating sets, okay, then the identity map from gamma equipped with the word metric coming from my first generating set to gamma equipped with the word metric coming from my second generating set. This guy here is a quasi-isomet. In fact, it's a bi-Lipschitz map. So my definition is gone. So a bi-Lipschitz just means that in the definition of quasi-isometric embedding, you just let the additive constant be 0. Okay. Okay. So in particular, if you're willing to consider metrics up to quasi-isometry, then on gamma you have this you have this well-defined object, well-defined class of metrics. Okay. Okay, so a consequence of this is now we can say what it means for the group to be hyperbolic, right? So definition. Okay, so first, a finitely generated group gamma is hyperbolic if CS gamma is hyperbolic, if its Cayley graph is hyperbolic for any or equivalently some finite generating set. S. Okay, and then you can also define the Gromov boundary of the group. Of gamma. Okay, which is defined to be the Gromov boundary of its Cayley graph. Okay, and this is something that's well defined. So now these objects do not depend on the choice of my generating set. Okay. All right. So this is my Gromov boundary of the group. Okay. Now I can explain what I mean by the north-south dynamics that I want. Okay. So this is usually called a convergence group action.
So I guess here the finite generation is like equivalent to properness. I never quite realized that. I mean, you can make the definition, and if it's not finitely generated, it's just not proper.
Finite things are compact.
Indeed. And that's Gromov's lesson, right?
Okay, so where was I? What was I supposed to do? I lost my train of thought. Oh yeah, north-south dynamics. Okay, so here's a theorem that's due to Tukia and Bowditch. Okay, which is that if you look at the gamma action on the boundary of gamma. Okay, so what is this action? So gamma acts on the Cayley graph of gamma by isometries, and we saw just now that when this isometry action extends to the boundary. So you have this action here, and this is a uniform convergence group action. Okay, so I'm not going to really I'm not going to explain what this means. In particular, I'm not going to explain the uniform part. Okay, but to be a convergence group action, what this means is that if you have a sequence gamma I in gamma, such that gamma I converges to a point A in the boundary of gamma, and the sequence of inverses gamma I inverse converges to some point B in the boundary of gamma, then for any point x in the boundary of gamma that is not B. Okay? And if you apply gamma I to this x, then this will converge to A. Okay, so the picture, you can draw another picture here.
A is not equal to B in your assumption?
No.
Yeah. No, I mean, that's an assumption, right?
No, A can be B.
Oh.
Yeah. Okay, but the the picture that maybe you should think about is that I want you have this sequence gamma i's. Okay, so this is supposed to be the picture of the boundary of the group. Then inside here is your group. So you have this sequence of group elements converging to this point A in the boundary. And you look at the sequence of inverses. Okay, which is the point B in the boundary. Then if you pick any other point X that's in the boundary of gamma but it's not B, and you keep applying your gamma i's. Okay, and this will eventually converge to A. Okay, so this is what I mean by the north-south dynamics, right, in section 0 on the boundary of gamma. Okay. Okay, so one last ingredient I need before we can talk about Anosov representations is the Gromov flow space. Okay, so again, I'm going to let gamma be a proper hyperbolic metric space.
What does uniform mean here? Isn't this just for the convergence group action or what?
Yeah, this is just a convergence group action. Yeah, so this implication. But uniform here just means that every point is a conical limit point.
Okay.
But I don't want to define that.
This is not the definition.
Yeah, this is not the
Okay.
definition.
Fine.
Yeah. Okay. All right. So okay. So the last one is the Gromov flow space. Last thing I need. Okay. So once you have this, if you have a proper hyperbolic metric space, then you can look at this set. At this point, this is it's a topological space U gamma. Okay, which is the set of pairs x, y in the boundary of gamma that are distinct times R. Okay, so this is U gamma. And on U gamma, you have a natural flow. So you have a flow on this space. And what this flow does is, if you take any point in this space, right, which is x, y, t, x, y, s, this sends it to x, y, s plus t. Okay, so you're just flowing in the R direction. Okay. Okay, and here's a theorem. Okay, I'm going to be very imprecise about this. So I think this is due to Gromov, but developed by Matthias and Champetier. Okay, so basically, I'm going to be very imprecise about this. Okay, so there exists a nice gamma action. Z2 action and metric on U gamma. Okay, so what does nice here mean? So okay, first thing nice means here is that if you take U gamma and you quotient out by the gamma action is proper and co-compact. So when you quotient out, you get a compact space. Furthermore, I want everything to descend. So the action here has to commute with my flow. The Z2 action also must descend, so it has to commute with the gamma action. There's some anti-commuting properties between Z2 and the flow, right? And then we'll reflect the metric also needs to descend, so the metric has to be gamma invariant. And then the flow lines have to be quasi-geodesics. So all these properties. Okay, but the point here is that what you get is a compact metric space, which I'm going to call U gamma hat, which is U gamma quotient by gamma. Okay, and this U gamma hat is going to have a flow, right, which comes from the flow on U gamma, and is also going to have a Z2 action. Okay, here. Okay, so maybe this might be a bit abstract, so let me give you an explicit an example. Okay, so if your gamma inside of isom Hn is a uniform lattice. Let's keep it simple. Okay, so for example, if you take n to be 2, you can take gamma to be a surface subgroup. Okay, then in this case, the boundary of gamma can be identified with the boundary of Hn. Okay, and this flow space U gamma can be identified with the unit tangent bundle of Hn. Okay, and the point here is that if you take any, if you're on the unit tangent bundle of Hn, you have the geodesic flow. Okay, and that is this is supposed to be, the point is that this construction here is supposed to be generalized this. Okay, and every flow line in the unit tangent bundle of Hn is the flow line is given by 2 points, right? A forward endpoint and a backward endpoint in the boundary of the group. Okay, and that's exactly what we are doing here, right? When we construct the U gamma. Okay, so this is your model on what this U gamma should look like. Okay, all right.
And Z2 action is just time reversing?
Yes, the Z2 action is you just take t to minus t, right? Okay, maybe I should point out that this identification is not canonical. It depends on a choice, some choice that you need to make this identification. Okay. Okay, I think I have 4 minutes left, so I won't attempt to push on to the next section. But maybe next time, for sure, I can give you the definition of Anosov representations, and we can discuss some other properties then. Okay, so I'll stop here. Thank you.
Questions, comments?
Maybe a comment. The reverse of this theorem is true too, right? With like all the conditions. So it's unique up to quasi-isometry such that the flow lines are quasi-geodesic.
That's a theorem like this. If you have a space with a gamma action and a Z2 action and a flow, and you have a bunch of properties that satisfy, then Gromov showed that they have to be quasi-isometric. Yeah.
I just missed what having the nice metric has to do with making. What is U gamma hat?
So what is U gamma hat? U gamma hat is defined to be this. You take U gamma and you quotient out by gamma. So okay, so in this case, U gamma is T1Hn, and then U gamma hat, yeah, maybe I should say that, is just the unit tangent bundle of Hn quotient out by gamma.
Then you could say how gamma acts on the first factor of the product.
How gamma acts
on the first factor of the...
Yeah, okay, so on the first factor. So here the gamma action, it has to take the flow lines between A, B to the flow line between gamma A, gamma B. So gamma of A, B, R has to be equals to gamma A, gamma B, R. Okay, but the tricky part is saying where the T parameter goes. Okay, so there you need to define something called a co-cycle to do this.
More questions?
Maybe just the theorem is not that this is, I mean, it's not only that this is a uniform convergence fraction, but that this characterizes.
Yeah, so that's the second part. So that's Bodish. It tells you that if you have a group gamma, if you have a M that is perfect, metrizable, and your gamma acts as a uniform convergence group, then it tells you the gamma is hyperbolic and this M is actually the boundary, yes. But this is a weaker version, okay?
I didn't understand why you need the last theorem of Gromov mutants.
Oh, I haven't told you how I'm going to use. You mean this one?
Yes.
I haven't told you how I'm going to use it, but I will use it in the definition of Anosov representations. Okay. Yes.
Okay, so if there are no more questions, let's thank the speaker again.